All right, guys. Today we're going to spend some time looking at something called function operations. And my hope is that when we're done, you'll not only understand what the notation of those function operations is, but actually how to successfully complete the operations. Now, it turns out there are 5 different function operations that we're going to be considering today. Several of these you potentially already know. Some of them you may not. So if you think about the idea of function operations, what's 1 or 2 or 3 or 4 or 5 that you think you know something about already? And there comes the silence.
Well, it's anything like the bell work, we're adding and subtracting functions.
Y equals B.
No. Any other operations?
Multiplication and division. The last one, exponent.
Unfortunately, it's not. These are operations that we perform between 2 functions, combining these functions. And so we can add 2 functions, we can subtract. And as was mentioned, it was kind of like our bell work. I gave you 2 functions. Here you added values of the function. Here you subtracted. Down here, we multiplied. And then finally down here, we're dividing. So there's those 4 function operations that we looked at. There's a 5th one. Don't go to numbers for this 5th one. It's not there yet. I just messed you up. What did you think was going on? Really, I think those things could fall under the category of multiplication. This is one that, yes, you've seen it. But no, I substituted in somebody's class the other day, and they were doing the same operation with Algebra 2 students. So, yes, you have been exposed to this, but it's probably been at least a year ago or a little more since you were last exposed to this concept. It's called composition.
Sounds like a composition notebook.
No, not a composition notebook. It's a composition of functions, and they are a little bit different. We will quickly review the first 4 just to make sure that you know what's going on. And please, if you struggle with one of those topics, we can do more examples. But I want to spend probably more of my time on composition because it sounds like not only do you not remember the name of that, I'm not sure that once we see it, you're going to remember how we do it. So we're going to spend a little time on that one. And just like last time, I want you to spend some time writing some notes to yourself about what works, what doesn't. That's part of why I'm also going back and talking about these other operations. Plus, I'm going to utilize some notation that may be slightly unfamiliar to you related to these operations here. But I'm thinking there is some background already, especially for the first few of these operations. So some things you should be able to accomplish. So let's consider the function f of x equals 6x plus 8 and g of x equals 2x plus 12. Use those. So let's try and find f plus g of x. And that does look a little bit different than your bell work yet.
Oh, that's something?
This is addition. I'm going in order of my list. So this is just addition. Now this is one way to notate it. Another way to notate it might be f of x plus g of x. Separate type of notation. That might be a little more clear in this second type of notation than it was in the first type of notation. But I'm hoping it kind of makes sense to say that 6x plus 8 plus 2x plus 12. And then what are you going to do? Well, 6x and 2x is 8x's. 8 and 12 is 20. Something like that. Does that make sense? Do we need any more on this topic? Okay, you ready for the next one? So let's see what you can do with f minus g of x. Let's see if we can be successful with this one. I'm seeing some head nods, yes. Do we all agree? Do we disagree? Do we need the details provided? What do you need? Yes?
If you put the G of X in parentheses and make all the numbers in G that's negative,
Yeah, so it would be 6x plus 8 minus the quantity of 2x plus 12. And yes, the negative changes both those signs. Okay? Not too bad, is it? All right, what was next?
Multiplication.
All right, so we might take g times f of x, with something like this. We might use what's called juxtaposition, writing them right next to each other to imply multiplication. You might see a solid dot there signifying multiplication. You will not see an x there. One or the other. That's about right. Does that match anybody else's multiplication?
Hey, this one I might get
Okay. 1001. Have we got a second of that?
Yeah, I got what you got.
You might need to see the details on how we do that. And so we're going to take 6x times 2x, and that's 12x squared. We're going to take 6x times 12, and that's then plus 72x. And we're going to take 8 times 2x, and that's plus 16x. And we're going to take 8 times 12, and that's plus 96. And then you collect the like terms in the middle. And that's going to give you, hopefully, the 88x. That look about right. And so you have different methods of doing that. You don't just have a multiplication out this way. You have a box you use. You have some other techniques you use, which is fine. We just want to successfully multiply. We're good? All right. So the next one, or maybe the last one that we're maybe supposed to know, let's say g over f of x. G over f of x. Something like that, I think. Does that look familiar to you? Uh-oh. Well, I could have made arithmetic error. Let's find out. So g of x, if we go back up here, is 2x plus 12. Put our memory banks. F of x is 6x plus 8. I bet you that's why it's not the same. But that should be 3x plus 4, and it's negative 4/3. That might look better. All right, let's put the details together. So 2x plus 12 over. And then you have 6x plus 8. The f of x function, is that right? So how many got there? You understand we get there. Okay. So then it's the now what?
Divide by.
Well, if I'm looking, there is a factor of the numerator that's a common factor. That's 2. Which gives me x plus 6 as the remaining factor. And in the denominator, there's also a common factor. In this case, it's also 2. Which is then 3x plus 4. And so now I have a series of factors multiplied together. And what is 2 divided by 2? So this is a 1, correct? So that means 1 times the fraction is just the fraction. So x plus 6 over 3x plus 4. But then I wrote this. X does not equal negative 4/3. How did I get that? What is that? So the denominator of 3x plus 4, we don't want to be 0, right? Because that's not a real number. So it's actually a domain restriction that we're putting in this problem when we're dividing. So we tell the reader, hey, you cannot let this be part of your domain now. Originally, we had two functions where the domain was all real numbers. Now we have a slightly more restricted domain, and we make a notation of that when this fraction is done. That's all it is.
How do we know that specific number is excluded?
Well, here's what I'm going to think. I'm going to think about that 3x plus 4 cannot be 0. Because if it's 0, it doesn't work. So then I'm just going to subtract 4 from both sides and say that 3x does not equal negative 4. And then we'll divide both sides by 3 and say that x then does not equal negative 4 over 3. But it's taking that denominator and saying the denominator cannot be 0. Questions about that?